we have discussed the gradient of a scalar field, which produces a vector field, and we have discussed the divergence of a vector field, which then again produces a scalar field. Those two operators together are already sufficient to introduce another differential operator, which is known as a Laplacian. So, let f be a scalar field in n variables defined on R to the n, then the Laplacian of that scalar field f, written as delta f, is defined as the divergence of the gradient of f. Let's briefly check what's happening here. So if we take the Laplacian of f, that means we take the divergence of the gradient of f. Now, f is a scalar field. The gradient will be a vector field. And if we take the divergence of this vector field here, again we get a scalar field. That's what we already know. So we can summarize as follows. The Laplacian of a scalar field is again a scalar field. I think in vector calculus it's always important to keep in mind what type of objects we are talking about. Whether we talk about numbers, or scalar fields, vector fields. So the Laplacian is defined on the scalar field, and by a combination of the gradient and the divergence, it produces another scalar field. Many of you might already be familiar with the Laplacian of a function, and you might even know an explicit formula, which is given in terms of partial derivatives. Explicitly, the Laplacian of f can be written as, we take the first derivatives, the derivatives in the first direction 2 times of f. Then we take 2 times the derivative in the second direction of f, 2 times, and so on. And eventually we take the derivative in the nth direction 2 times of f. That is an explicit formula for the Laplacian, which I think many of you are familiar with. As a very short reminder, let's do one example. Let's suppose a scalar field f in 2 variables is given just by x1 squared times x2 squared. What happens if we take the Laplacian of this? Well, the Laplacian of f at x1, x2. For that we take the derivative in the x1 direction 2 times. That gets us 2 times x2 squared. And we add up the derivative in the x2 direction 2 times, giving us 2 times x1 squared. Voila, that's the Laplacian of this simple function. The Laplacian seems quite simple. Nevertheless, I would like to discuss one more example. In particular, I would like to demonstrate that both definitions of the Laplacian, either in terms of the divergence of the gradient or by adding up second derivatives, lead to the same result. So let's suppose we've got a scalar field f given in 2 variables, x1 and x2, and it is defined as the sine of x1 times the sine of x2. That is a very simple definition of a function, but in fact it's also a quite important example. For example, when we discuss the Laplace equation, let's say over a square, then such functions are of tremendous importance. So let's first do the definition of the Laplacian using second derivatives and apply this to this function f. We begin by writing down definitions. the Laplacian of f at x1 and x2 equals, by definition, take the derivative in the first direction 2 times, plus take the derivative in the second direction 2 times. Let's do one after the other. We get del 1 of the cosine of x1 times the sine of x2 plus del 2 of sine of x1 times cosine of x2. Let's do that once more. We get negative sine of x1 times the sine of x2 minus sine of x1 times sine of x2. In summary, we get negative 2 times sine of x1 times sine of x2. Later on, when we discuss the Laplace equation over a square, then functions of that form or similar form are quite important because they are so-called eigenfunctions of the Laplacian. What we observe here, just as a comment, is that if we apply the Laplacian to the function f, well, we get actually the same function f again up to some coefficient, in this case negative 2. That is very similar to so-called eigenvectors in linear algebra, which I presume you've already seen in previous classes. Now, just for practice, let's do the same example again, but this time using the definition as the divergence of the gradient of f. Let's again write down definitions. This time, we take the divergence of the gradient of f Let's first compute the gradient. So we have the divergence of, well, of course, cosine x1 times sine of x2. It's the first component. And we've got sine of x1 times cosine of x2 in the second component. And now we just compute the divergence of that. Once more, we get sine of x1, negative sine of x1 times sine of x2. And once more, this has been the derivative in the x1 direction of the first component. Now we take the derivative in the x2 direction of the second component. And then we add negative sine of x1 times sine of x2. And of course we get the same result. Negative 2 times sine of x1 times sine of x2. Both possible definitions of the Laplacian are important, and depending on circumstances, one might be more convenient to work with than the other. I would like to comment very briefly on some motivations for the Laplacian. Generally speaking, the Laplacian is the differential operator that appears in many important partial differential equations in physics, engineering, and mathematics. One possible example is the heat equation. The heat equation describes the diffusion, for example, of heat inside a domain over time. It can also describe other diffusion processes such as, for example, chemicals and water. We can write down the heat equation in a very simple variation as follows. We've got the time derivative of some quantity, let's call it u, which depends on time and space. The time derivative of u shall equal the Laplacian of u. here the Laplacian is only taken in the space coordinates. In this case, U is a scalar field that describes the density of, for example, heat over time and in space. The heat equation tells us that the time derivative of U at position x and time t, which means given a position x at some point in time t, how does the heat concentration change in time? That change in time equals the Laplacian of U at the same position in time and space. It tells us that the change in time of the heat concentration at xt equals the Laplacian of U at the same position in time and space, x and t. This is only a brief interjection, so to speak, as a motivation. This will be discussed in much more due detail later on in the class.